talk about gravity. There's going to be a lot of talk of gravity. And the idea of, you might, and centrifugal acceleration, the idea of things go around in circles, and you might think, well, where's that coming from? Why are we talking about gravity? Why are we talking about centrifugal acceleration? But it turns out that one of the main sources of centrifugal acceleration, or the force associated with centrifugal acceleration, is the gravitational attraction between bodies. So we need to see if we can talk about that. Okay. The issue with gravity is that being this close to the Earth is that we can't escape it. Okay? Even if you go up in the space shuttle, okay, you see all the photos of all the people bobbing around, is that you cannot escape gravity. All of the people within the space shuttle are still under the effects of gravity. It's just that not only are they experiencing acceleration due to gravity, but their entire surroundings are experiencing acceleration due to gravity. Okay, let me ask you a little something. If this is the Earth, right, and this is to scale, and the Moon would actually be about this big. That's this one, the man and the Moon. The relationship roughly between the Earth and the Moon is about that. Now, if this is to scale, how far do you reckon that this is from here? Is that too far away? Is that too close? What do you reckon? Tell me. I'll keep walking away and you tell me when to stop. Okay? Or you put your hands up when you think that we're there. Okay? So, thank you, Maddie. Oh, Thomas is there. Is it that far away? Oh, got Andrew out here. Oh, Thomas is there. Toby's there, sorry. Cool. Some people haven't put their hands up yet. It's going to be far away. Anyone? I'm running out of room. The answer's about there. The answer is about 8 metres. We worked it out about 2 years ago. We actually worked out the scale of this. So there you go. The Moon, on which 12 people have stood, and about, I think it's about 18 people have been to, including the people who have flown all the way there and flown all the way back again. Okay. If you want to get up, if you want to stand somewhere where you can actually block out the entire humanity with your thumb, then you need to be standing this far away. Because apparently the other one of the things that blew the astronauts away is just looking back at the big blue Earth and then holding up their thumb like that, and they could block out all of humanity. So it's about there. If I'm in the space shuttle, use my thumb in the space shuttle. Oh no, hang on. If I'm in the space shuttle and I'm flying out from the Earth, and I'm going to the International Space Station, how far out do you reckon the International Space Station?
very far.
Not very far? So, am I far enough yet? Am I too far? The answer is it would barely be off the surface. It's about 300 kilometres. It's about the distance from here to Devonport. If you're going to go to the space station, and that's going round and round the Earth very quickly. Now, you can imagine. The Earth's atmosphere. If you've got an Earth this size, how thick do you think the Earth's atmosphere is?
200.
Barely the thickness of the coat of varnish. So bear that in mind next time you're pumping stuff into the atmosphere, is that if you look at it from side on, you can barely even see it when you're out in space. Because it's so thin, this little envelope of gas that protects us all is, if I were to put an extra coat of varnish on that, that would probably be about to the end of the edge of the atmosphere. So there you go. The moon's over there, it's about 8 metres away. This is about the size of the Earth. The moon's about that big. And so the idea of gravity, two massive bodies, and the fact that the Earth, the moon is rotating around the Earth in a circle, so it must have, if it's going around in a circle, it must have centripetal acceleration towards the centre, and that centripetal acceleration is provided by an unbalanced force, and that force is going to be the gravitational attraction between these two massive bodies. There's no contact, there's no piece of string, it's a non-contact force, and that force is such that it's actually going through there and around there. In the same way that the Earth orbits the Sun, there's going to be a gravitational force between the Earth and the Sun. There's a gravitational force between everything. Toby and Alexander, for instance. You're feeling very, very minute over that distance. Okay. Or Andrew and Mandy. I like picking up, Couldn't do it last year, there were any girls in the class, but that's right. No, sorry, the year before. There were no girls in the class the year before, so I could actually start to make all sorts of inappropriate suggestions to that. So what's happening here? How do we get this? You can buy, if you've got a spare, or this is back in the day, if you've got a spare $4,000 US, okay, is that you can go on a weightless flight. And you've all seen Apollo 13, and Tom Hanks is flailing around there, floating around in 0G. And we can actually produce it and use this for, so he's a guy in his spacesuit training. I hope he's training, otherwise these guys are all in a lot of trouble. He's the only one with the proper spacesuit on. But they're sort of going up there and taking little bursts to go through from there. So, gravity. How do we actually do that? How do they actually form these periods of no gravity? So what's actually happening here is that you get on your trusty A300 Airbus and you go up, and this is affectionately known as the Vomit Comet, and there are a series of these things around the world where you can actually go and do training in zero gravity. And we say do it in zero gravity because it goes for about 22 seconds. There's a period when the plane's going up and pulling a curvature like that, so that the everything in the plane is actually falling back to the Earth, and everything in the plane is falling to the Earth at the rate of gravity, so that the gravity is acting upon everything equally for about 20 seconds, and so things float around in space, float around as if there is no mass, no gravity. But what happens is when you pull out down here and pulling back this way, and your centrifugal acceleration is going back towards the centre here, that's working against gravity, and all of a sudden you feel twice as heavy as you should do. And you can do all sorts of things like that. And they do this again and again and again, so you get 20 seconds of weightlessness and 20 seconds of, makes you feel very sick. So these people actually, I don't know what the hell is going on here, but they decided they're going to do surgery in 20-second weightless bursts and see how they're going on. Yeah, right. Whoops. Done it twice there, haven't I?
astronaute de l'Agence spatiale européenne, l'ESA, et aussi président-directeur général de Novespace, une société privée, filiale du CNES, le Centre national d'études spatiales, qui, avec l'ESA, finance principalement ce programme de vol en apesanteur sur l'Airbus 0G. Cet avion est piloté par les équipages du Centre d'essai en vol de la Délégation générale pour l'armement du ministère de la Défense française. La maintenance est fournie principalement par les équipes de Techtonics installées aussi à Bordeaux, à côté de l'établissement de Novespace. Nous commençons la manœuvre parabolique par une ressource. Pendant cette ressource, nous pesons très lourd dans l'avion, presque 2 fois notre poids. Regardez la bouteille qui redescend très vite. Il faut comme ça attendre jusqu'à 60 degrés d'inclinaison. Nous entendons l'inclinaison de l'avion. 40 degrés d'inclinaison. Injection. Commence la période d'apesanteur, exactement la même période d'apesanteur que les astronautes dans l'espace. Pendant 22 secondes, nous flottons, et puis les scientifiques autour de moi effectuent de la recherche impossible sur Terre. Ils recherchent des phénomènes en apesanteur, que ce soit sur les fluides, les matériaux, les sciences de la vie, le comportement du corps humain. Et à la fin des 22 secondes, nous redescendons, et à nouveau nous pesons 2 fois notre poids pendant la ressource de sortie pour remettre l'avion à l'horizontale. Novespace est propriétaire de cet A300, c'est un Airbus construit en 1973, mais qui est très jeune puisqu'il a moins de 5000 heures de vol. Nous effectuons environ 30 paraboles par vol. Entre chaque parabole, nous avons un palier d'environ 2 minutes qui permet aux expérimentateurs de reparamétrer, réajuster, régler leurs expériences en vue de la période suivante d'apesanteur, qui, je vous le rappelle, dure environ 22 secondes à chaque fois. Nous sommes à 30 secondes. Et voilà, je commence une nouvelle parabole. Alain va me faire tourner en apesanteur, un peu comme les astronautes le font lorsqu'ils découvrent pour la première fois cet état très étrange dans l'espace. Il n'est pas besoin d'aller dans l'espace pour être en apesanteur. Et voilà. État d'apesanteur, exactement le même état d'apesanteur que les astronautes. Venez à bord. Et on se repose. À la prochaine.
Well, there you go. So, quite a young year, but I reckon it's done some. I reckon they might have done many air miles, but they'd be pretty tough air miles going up and down, up and down, up and down. I wouldn't be in the market for that one. It's a second hand one. Okay. So, we've got the pathway going up and the parabola is weightlessness, and then comes down here and you have double weight and weightlessness, periods of up and forwards, like that. So that's the idea of gravity. It's all around us. What's going on here? This takes me back to a time when I was not much older than you people. I just finished university. Started off during university, during the summer months. I used to get work for the mines department in Tasmania and go and work over there as a field assistant. I got allocated to the geophysics team, and we used to go around and measure gravity. Okay? And you say, well, what do you mean measure gravity? It's 9.81. Gravity changes. You get down to the 4th or 5th decimal place, and depending on how you go, depending on the rock types, depending on your environment, then the microgravity will actually vary about that, and you can actually use that to detect such things as using magnetic devices, a pretty old classic computer here, gravitometer, gravity meter. Well, there's a more modern one. This is the pride of the 1990s, the gravity meter, fully automated. Actually go around and use that, and due to the different densities of rocks, granites are less dense, diorites are more dense, and other using the very physical properties of different ore-bearing minerals, you can go around there and map the Earth geologically without having to go down there under the ground and look at it. So here we go. The old classic, the thermos, we used to call these. They've got a very fine silica spring, and you set those up, and then you set those on the ground, and you just have to keep very still, because the slightest movement, so people walking over the other side of the room, cause this spring to become unsettled and have to settle again. There's another one here. They've also got mapping now. Since I got out of the industry in the late 90s, they've actually developed systems where you can actually mount these on aircraft and go backwards and forwards and do sorties backwards and forwards across the respective area and come up with areas that are of higher, and this is a false colour map. This is over somewhere in South Australia. Now if you have a look here, you can see that the ground has got very thick regolith, it's called, up to 100 metres. This is old weathered material. There's no outcrop here, you can't see what the rocks are like, and it's got saltbush and all that, so you can either go, the alternatives are drilling down, which is very expensive, or you use geophysical techniques to try and determine what's underneath or narrow down where you want to drill or where you want to dig in order to find new minerals. So what we have here is what you would look, if you just had an aerial photograph, you would just see thin scrub and this brown dirt. But by going backwards and forwards and mapping us up, you can see here that the gravity varies from more dense to areas where it's less dense down over here. So these would be pods of granite coming up, maybe it could be pods of granite coming up if it's prospective, that sort of thing. And what happens is if you've got sedimentary rocks, sandstones, we're a little bit familiar with the basic geology. There are three different types of rocks. There's igneous rocks, which are forced, a bit like volcanoes, or come from molten rocks that come up through the earth. You've got sedimentary rocks, which are laid down in rivers and then compressed, and then there's metamorphic rocks, which are primarily sedimentary rocks that have undergone pressure and heat to change their format in that sort of regard. And minerals, if you're looking for gold, if you're looking for copper, if you're looking for nickel, if you're looking for all these things, they tend to get flooded through rocks, being driven under high pressure, high temperature, by various orogenic events. Orogenic meaning mountain building, so big geological events over a very long time scale. So for instance, this might be a granite, and if you know that this is a sandstone, the idea is a granite next to a sandstone is very prospective. for a mineral, for minerals, because what happens is that the granite comes up through the earth, forces the heat and the pressure forces water to go through the porous sandstone, for instance, and there might be some structural blockage there which causes the metal that's going through the fluid to get trapped, and that causes a spot where minerals collect, and that's where you go and dig, and you dig it up, and that's where the ore is, and you take that away and process that and produce metals. So the areas on Western Australia, those big gold fields, those big flats where it's just basically ripping up iron ore and shipping it off to China, all that areas occurred through this. The west coast of Tasmania is very rich mineral assemblage. It's got very high class, world class mineral deposits for a variety of different minerals. You've got copper and a bit of gold at Queenstown. You've got what used to be the world's biggest underground tin mine at Renison Bell. You've got lead zinc mines at Rosebery and at Zeehan. You've got silver mines up there, Avery gold mines up there. Keep going up the west coast. So you've got a tin mines, all sorts of different types of things. They've got a whole wide range. They've got very large, very rich deposits. The only issue is that they're pretty inaccessible, and they tend to be under a great deal of overburden. So things like the old conglomerate up there, which are very hard, very tough to get through, and very difficult, make mining very difficult, and make exploration very difficult. So it gets to the stage now where it's actually out on satellites. You can put a gravity meter out on satellite and do gravity maps of the whole world, including the oceans. Look through the water and look for variations in the Earth's crust due to different densities, and it gives you a bit of an idea about what's actually happening in this place. So there we go, gravity anomalies around the Earth. What we see is that there are, big gravity anomalies down the west coast of South America, for instance. Have a look up through here, up through the Philippines and up through Japan, all through Indonesia, certainly through the Himalayas and up through southern Europe. Some pretty interesting stuff up through there. Through the Atlantic here, there are some areas where it's quite low density. So we can see all this. We can see this variation in rock type simply from the variation in the gravity that we see. Now, areas like through central Russia, okay, the anomalies, these are milligauss, so these are quite very small, 800, total variation of 800 milligauss, and a milligauss, I used to know that, is down to about 1,000. So you got 9.81, and you got another couple of decimal places before you get down to determining this sort of thing. So what's actually happening here? So if we have a look here, and these white patches here that they've drawn on are very interesting, because these are areas where there are low. This one's, the red's actually low and the blue is actually high. So these are high density areas through the continental areas. There's down through this area, down through south of Australia, and up through the Pacific through here. You can see here that's quite thin, and there's variation there. Oh.
Because of the Earth's shape, and it has the flat spots on the top, not actually flat, but it's less, would the top and the bottom be much more greater in gravity than the equator?
Not that you would notice, but yes, because does actually widen a bit because the spinning of the Earth makes it a bit fatter at the equator than it is at the poles. So if you are at the equator, then what's going to happen is that there's going to be an increase in gravity compared to the poles, but there's also going to increase in increase in gravity depending on your altitude as well. And that's going to so if you're closer to sea level rather than up in the mountains, then you're going to have a variation in gravity as well. So, also, other than just looking for, to rip the goodness out of and turn into metals, we can also get a bit of an idea about what's happening within the Earth. Okay. This is the Earth. So anyone do maths applied last year? Can tell me what the radius of the Earth is? 6,371 kilometres. Do you know how far we've drilled down? The furthest we've gone?
I think it was 11,000. It's just deeper than the deepest trench in the ocean.
Yeah. 12 kilometres. So we've got a way to go. So, what's happening here is that on the surface of the Earth, we have the crust, which at continental thickness is about 40 kilometres, and over the oceans is about 5 to 6 kilometres. And then we have this mantle, which is a semi-liquid area coming down through several thousand kilometres. And then we have the outer core and the inner core. The outer core is a liquid, okay, high temperature, high pressure, but when we get down to the inner core, it's even higher temperature, even higher pressure and temperature, so that what happens in the largely nickel iron core is actually going to be solid at that point. And it's very important that this is liquid and this is solid, because that gives us, and we'll see this later in the year, it gives the Earth its magnetic field, which allows us to survive constant deluge of cosmic rays coming from the sun. Okay. Now, we have this mantle. So we have 1, 2, 3. How do we know that we have these distinct separate layers? If all we can do by drilling down go a maximum of 12 kilometres, and we've still got the majority of the 6,371 to go. Well, I'm glad to know. And what we also find is that as we go around the Earth, we have these areas where we have active volcanoes, the idea of plate tectonics, and the Ring of Fire, the Pacific Ring of Fire, but we have all these other areas as well. So we have through here the red dots are they earthquakes or are they active volcanoes? Well, pretty much both. And what you find is that there are areas on the Earth where volcanism is particularly active. So, for instance, if you come down here, down the western side of the Andes, that you get a lot of volcanism right on the western side of the Andes. And as you come across to the eastern side, over here, where they're sitting on their beaches in Ipanema and stuff like that, you don't get so much. You'll notice that as you come through southern Europe, through Italy, if you've heard of Payne, there's a very active volcano there. Hasn't actually erupted since 1944. And if you come down this whole area down through here, the Iceland is nothing but volcano. Okay? From a geological point of view, Iceland is an infant. It's nothing but volcano, it's nothing but basalt, and it's formed right there. You come out into the Hawaii, right here in the centre, and that's nothing but volcanoes as well. Now, as you come up through, there's certainly earthquakes up through here, and getting over through Alaska, and down here into Japan, earthquakes and volcanoes again. And then down through Philippines and down through Indonesia and down into New Zealand, again, earthquakes and volcanoes. Australia, very few earthquakes, relatively. No active volcanoes. The last active volcano in Australia was in Victoria, and you don't need to worry because I think it went off about 20 million years ago. Okay. So what's going on here? Why do we have some areas that are particularly active in terms of earthquakes and volcanoes, and we have other areas? The eastern side, the western side here has lots of the United States has earthquakes. Over here, not so much. Why are there areas that are particularly prone to earthquakes and volcanoes, and why are they the areas that aren't? Why are some random, and why is it random, or is there a pattern behind it? Well, it's not random, and this is only when I say a relatively new consideration, is that up until about 100 years ago, is that what's been proposed now and what is readily accepted was there was one bloke fighting for it, Wenger, and everyone else was fighting against it. So you can see here there's the ocean floors, and you can see here that these lines that go through, coming through underneath Australia, going up through the Pacific, and certainly up here through the mid-ocean ridges of the Atlantic. There's something going on here. Now you can see here, particularly this bit, if I drew that back over here and drew that back over here, they fit together quite nicely. The west coast of Africa and the east coast of South America fit together as if they were pieces of a jigsaw puzzle. And so what's actually going on? And so this is the idea of plate tectonics. We're going to have a look here. What happens is, people weren't quite sure what was going on, but over geological time, it's now worked out that we've got sitting on top of the mantle, this liquidy mantle, the solid crusts, and what they are doing is they're floating around like lily pads on a pond, okay? They're bashing into each other, okay? They're pulling apart from each other, and when they're pulling apart and bashing, they're sliding along next to each other, and when they're doing this, they're causing things to happen. So if we're having a look over at a situation like here in the mid-ocean ridge, between Africa and South America, Africa and South America are moving away from each other at about the same rate as your fingernails grow. Okay. Now, as they are pulling away from each other, what's happening is that they're causing a rift down through here, and it's causing a seam down through here, and if you pull that away, what's going to come up underneath it? You're going to have a string of volcanoes going through here, and new material is going to come up. Okay. And this was fiercely debated by scientists about 100 years ago, saying, this is rubbish, you cannot do this sort of thing. If only they'd been talking to the people who were putting in the new telegraph lines. Okay, new telecommunications between Europe and America, they were running cables along the seabed, out of ships, running along here to go from here so they could converse between here. After a while, they were breaking down. And what they did is when they pulled them up again, they found out that there were these rocky concretions attached to these as they were going across here. This rock was pulling up. And they're getting tighter, a little bit tighter every time, because Europe and America were actually pulling apart from each other. So the people who were putting these lines down were well aware that this was all going on. They just hadn't been talking to the scientists, or the scientists hadn't actually been talking to them. It took a while for that all to come together. But you're saying, how can, if these things are pulling apart, well, they're going to be bumping into each other? Where's the evidence for that? Well, have a look down here on the west coast of, say for instance, we'll have a look at the area down here, and we have a situation like this. If this area here is South America and this is the west coast, then what we have is that we have two continental plates, or we have two plates coming together. This side is the ocean plate, it's quite thin. This one here is a continental plate. It's built up, it's crushed up like that, and it's quite thick. And when that comes together like that, what's going to happen here is the little one is going to go down here and be subducted or come down beneath this one and be pushed down beneath this one which is going to the right. Now what happens when that does that is that the forces involved here are pushing this material down beneath it. And as you're pushing down one beneath the other, pressures build up, pressures build up, pressures build up until it gives way. And it gives way, what happens?
Earthquake.
Earthquake. Now what they're saying, well, if we expect that, then what we would see is that the focus of the earthquake, with an earthquake, we describe as having a focus and an epicentre. The epicentre is the point on the surface directly above where it is. The focus is where it is in the ground, that is the source of the earthquake. On here on the west coast, you find that the earthquakes are quite shallow. As you get further and further and further inland, these earthquakes are getting deeper and deeper and deeper. As they're coming down through here and they're grinding up, they're forming these, the heat is building up and they're forming a magma generation. And what's happening here is getting partial melting. Some minerals melt at lower temperatures than others, and they tend to be lighter coloured minerals. And what that does is it forms, so the darker minerals get carried down, the lighter minerals get pushed up through here. And as they get pushed up, they are blockier, they don't flow as well, they build up here, and they push up here to form volcanoes, and they form a rock here called andesite. What do you reckon they call it, andesite? Where did they find it? In the Andes, that's right. So right here in the Andes. And it is blocky and it explodes, and it's a volcano that explodes. It doesn't give away gently. It's the sort of volcano that's going to explode all through here. Like the one that's on this, in 1980 in Mount St. Helens in Washington State. They had no idea that it was going to go off, to the extent that there were about half a dozen volcanologists working on the side of it with machines going, oh, what's going on here? This seems a bit odd. They all got killed. Okay. So that was all going on. So this is what's going on here. So this is all evidence that this is all going on. What happens if you have a continental plate meet a continental plate pushing together like that? What happens is it pushes up, pushes up, pushes up, pushes up. So if you've got a plate, say India for instance, ploughing into the large Asian plate, then you're pushing those together, and you get mountains, range of mountains falling out the top of that. What do you reckon they call that?
Everest.
They call that the Himalayas. Okay? So, where we have oceanic plate meeting continental plate, it pushes down underneath and we have this subduction zone and we get lots of these. Similarly with Japan. Okay? The Pacific plate is coming under the Asian plate and we get lots of earthquakes and we get lots of volcanoes. Not recently though. Normally it goes and has a whole series of earthquakes. Tokyo hasn't had an earthquake and is well and truly overdue. Well and truly overdue. When it goes, and however many people are living in, how many million people are living in Tokyo, it's going to be catastrophic. Here we have, you might have heard of the idea of Gondwana land. So this is like during the Permian time, which is 225 million years ago, all of these things were lumped together. And then what did we get? Is that we had started to get separation, so about 20 million years ago into the Triassic, is that these things start to break up a little bit. And you can see here South America, there's Africa here, India is coming up here, going to smack up into here very soon. This is during the Jurassic. Now during the Jurassic is a particularly important time for Tasmania, because that is the time that a lot of dark magma came up from underneath the earth, okay, and forced its way through the existing Permian. These are geological ages. Forced their way through the rock beds, okay. Huge, great big sills of igneous material. It wasn't volcanic. It didn't come. Volcanic means coming out to the surface. but these ones didn't come out of the surface. It came up and forced its way through and made kilometres of thick igneous material, dark igneous material, and cooled down reasonably slowly so that the crystals were getting quite a size. It wasn't like they weren't forming granites or anything like that, but they were forming dolerite. And so a lot of the, and then since that time, the rocks on top of ground have eroded away because they're softer, and the ones that are left behind are the dolerite that we see on Mount Wellington and throughout much of southern Tasmania, southeastern Australia, Tasmania. So down through, you'll see it down through the Tasman Peninsula. If you go down there and go to Cape Hoy and such things, then you'll have a look at those sort of things. So gravity. Alright, well we'll stop that there for today, and we shall, so you got your test on Thursday, and we'll see if we can't do a prank on Thursday afternoon just around there. Okay.